Hi, and welcome. Thank you for joining the Consulting Specifying Engineer webcast, Critical Power, Generators and Generator Power System Design, sponsored by Pritchard Brown, ASCO, and Kohler. I'm your moderator, Amara Razgas with Consulting Specifying Engineer and CFE Media and Technology, and I'll be with you during this hour-long webcast presentation. To learn about this platform, please listen in. If you're having trouble with your slides or with the sound, refresh your internet browser or click on the Refresh Media button directly under the presenter's photo. You can control the volume settings by adjusting the volume on your own device. If you're having technical problems, please click on the question mark at the top right corner of your screen to do a system check before contacting an online technician. But if you do need help, please type a message into the Ask a Question box and we'll respond in the Answered Questions box. To download the presentation slides, use the Event Resources tab on the left side of your screen. To type questions for the presenters, use the Ask a Question box on the left side of your screen. You may ask questions at any time during the presentation, and the Q&A will start in about 45 minutes. If you're interested in receiving one AIA CES approved learning unit, for this event, you need to pass a 10-question exam. To take the learning unit exam and to download your AIA CES certificate, use the Learning Unit Exam tab at the top of your screen. The quiz will open in a new browser window, so I recommend that you open a new tab right now because the link will break when this webcast signs off. In keeping with the American Institute of Architects Continuing Education System Policy, please take a moment to read the quality assurance slide. Here are the learning objectives. We'll talk about these in today's presentation. Please note that any red underlined text that you see is a hyperlink in the PDF where you can get more information. Now let's hear from today's session sponsors. At the conclusion of the commercials, you may experience a few seconds of silence to make up for mixed internet speeds. Please stay tuned after the video for today's presentation.
For over 70 years, Pritchard Brown has built a gold standard in custom on-site power equipment enclosures. Our dedicated design professionals work with clients from start to finish to ensure that the most critical part of the on-site critical power installation works, shines, and lasts. Our tailored enclosure solutions protect your equipment, meet your specifications, and stay on budget. No matter the challenge, noise control, space constraints, wind and seismic loading, Pritchard Brown has the solution. When it has to be done right, call Pritchard Brown.
Time for another road trip. ASCO's mobile classroom shows critical power solutions to partners and customers across the U.S. See the touch display interface, load banks, and communication devices. Even ASCO's 7000 series bypass isolation automatic transfer switch, up close and personal. Valuable on-site education, interactive 3D product and market solutions, along with immersive virtual reality experiences, are also available. ASCO Power Technologies Mobile Classroom. Coming soon to a location near you.
Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engines running. Commit. Liftoff. We have liftoff at 11 a.m. Eastern Standard Time.
All right, well, we've lined up two exceptional presenters today. First, Brian Renner is a principal engineer and the mission-critical leader at Smith Group, with experience as a manager, director, and engineering leader in the design of numerous types of facilities. He has a passion for mission-critical and science and technology facilities. He is a longtime member of the Consulting, Specifying Engineer Editorial Advisory Board, and he's been contributing articles and presentations for about 30 years. Daniel Flaherty is a mechanical engineer at CDM Smith with experience in designing, construction, and commissioning of engine, generator, and building mechanical systems. He's worked in manufacturing facilities, water purification, and wastewater treatment facilities, laboratories, and remote electronics facilities. He's a licensed professional engineer in several states and is a certified commissioning professional. All right, I'm eager to get started. Brian, you're our first presenter. You're live now.
Thank you, Amara. So we're going to cover a couple topics today. Obviously, we can't go to the depth we'd like to on all the topics, but we will cover enough for you to understand where to go for more information as you design generators and generator power systems. We're going to cover basics and codes. We're going to cover electrical considerations, electrical power design, considerations for generator. We're going to talk about mechanical systems, including cooling and fuel systems. And finally, we'll end with a little bit of coordination with our fellow design team members, including architecture and structure. So let's first talk about the components in the generators. We call them generators, but really there are both primarily an engine and a generator component. There's a radiator and there's controls and breakers. These are important to understand because although from the vendors you will get a standard package, it is possible to consider different engines and different generator changes when you're specifying engine and generators. So this will help you get an idea of where the components are. For instance, the radiator may be mounted on the generator or it may be remote mounted, but typically it's located on the generator. So let's talk about NEC code classifications. We talked about the fact that a generator is really an engine generator, but we also tend to often in meetings with clients and representatives talk about emergency, the emergency generator. Well, there are very specific requirements in the National Electrical Code on what emergency generator is, and that's covered under Article 700. Basically, these are systems, loads, that are required to supply illumination and power that is essential for safety to human life. Typically in a facility, this is going to include egress lighting, fire pumps, elevators in high-rise buildings, and fire alarm systems. Under emergency generators or emergency systems, you're required to have a 10-second start time on the generator. The wiring itself to these emergency loads, emergency classified loads, has to be separate from other types of loads. Next, the generator may be applied for legally required standby loads, which is covered under Article 701. Typical examples of what might be legally required are local authorities having jurisdictions, other state or local agencies, and can include things like HVAC, ventilation, smoke removal, sewage and sump pumps, and communication systems. Here, these systems are less critical than emergency and can have a 60-second start time. Lastly, we have optional systems. These are critical operations that, or owner's wish list, things that they want to have operate or may cause them severe financial or other issues. Examples could be data centers, could be executive suites, building occupant comforts that are required for the continuation of the building, or just simply an owner who has had frequent utility outages and wants to back up certain parts or all parts of the building. And lastly, we have under the National Electrical Code, healthcare facilities. This can be a presentation all in itself, and those are covered under Article 517, and they have much different classifications for the different systems. So what are some of the newer things that we've been dealing with regards to the electrical code with generators? One is a temporary source of power, which is covered under Article 700.3 when it's an emergency generator or classified to power emergency loads. It's always been good practice to have a hookup box, not only for a temporary generator should the generator fail, but also to do load testing should you not have a permanent load bank required. But now NEC requires these for emergency systems. So it's not just good practice, it's mandated when you have emergency systems. This hookup box will typically be located externally to the building, weather-tight enclosure, and they are combined so that they can both be used for a temporary generator should the generator be down, or as a load testing box. Notice that the NEC talks about should the generator be down for maintenance. If you have multiple generators, say N+1 redundant units, multiple parallel units, where any one generator can fail or go down for maintenance, these may not be required, but you'll have to check with your local authority. The next section that's new or newer to the National Electrical Code is control circuit integrity. And this is also, again, applies to emergency generator systems, where it's basically you're going to have to monitor and prevent the failure of control circuits. The days of a pair of wires for your ATS or for your generator controller are gone. These are multiple wires with different types of monitoring should there be a fault or should there be cut or interrupted. So let's talk about some of the sizing considerations. One thing that as a young engineer was kind of a learning experience for me is you see generators rated in kW or kVA. You might see a 2000 kVA generator. As electrical engineers, we tend to focus on kVA as the total power. But it was interesting to learn when I was a young engineer that generators continue to have a 0.8 power factor rating. So what this means is most modern facilities these days are 0.9. Data centers might even unity or leading power factor. Hospitals, high power factor, because of all the electronics, the VFDs these days, we don't have that low power factor. What this means is its generators are kW limited. Basically, when you look at the size of the generator, your safest bet is to use the kW rating and not the kVA rating when you're choosing the size of the generator to match the load you have. Second thing you need to understand is demand and diversity. We talked about those load classifications, emergency, standby, optional. The emergency loads have to be calculated at 100%. You cannot apply demand and diversity to the life safety systems, to the things that are essential to life safety. Next, you really need to look at the types of loads that you'll be putting on the generator. These include large motors, fire pumps, and transformers that might be transforming from the generator down. There are voltage drop requirements, particularly for fire pumps. The generator is not like the utility. It doesn't have that robustness, that ability to handle loads starting on it. The generator is much smaller. The easiest way to do this is with the generator software. Most of the vendors have free software that's available. Your firm may also have software that you have purchased to be able to do this voltage drop and generator starting and motor starting. The UPS systems in the old days used to have to size the generator 2 or 3 times the size of the UPS. That's because the UPSs were not designed with particularly clean input power. The generators had trouble handling that kind of electronic load. That's really changed. UPSs are much better. You still need to check with your vendor UPS and generator to talk about compatibility. You can model that in the software. But in addition, you need to look at the window when the UPS goes to battery and when the generator comes on, because generators may allow a little dirtier power than the UPS wants to see from the utility. And you don't want your UPS going to battery while you're on generator. Lastly, for consideration on sizing, make sure you understand the site altitude and temperature constraints of where you're placing these generators, particularly when they're outdoors, and check with the vendor about any D-ratings based on the site altitude or temperatures. So let's talk about generator ratings. You see a 2000 kVA, or in this case, 2700 kW generator, and you figure, well, how am I going to apply that? It's an emergency. Am I going to use it for a data center? Am I going to use it for prime power because the owner wants to be able to put the facility on generator power for whatever reason, utility rates or whatever? Understand that generators have different ratings. Typically, it's an emergency standby rating, as you can see in this chart, where the rating will be for a certain period of time, a certain rating, but after time, it may be derated. This is why you see the different ratings here. For instance, on data centers, data center rated generators are rated for the full rating of the generator, and they're rated for the full rating of the generator if you continue to use it beyond 24 hours or even longer. So make sure you understand the application and what the ratings are. Next up, you're going to be probably applying automatic transfer switches. It's possible to have the generator go right to the switchgear, but in most cases, there's automatic transfer switches involved. You basically transfer between the normal power and the generator power to load. Understand the space requirements and the type of switch you're doing. Smaller switches, 400 amp, 200 amp, 800, even 800 amp, those don't require much space and can be wall mounted. The larger switches may require rear access, which is a learning experience I went through as a young engineer to understand that a 1600 amp automatic transfer switch may need rear access. You also have to discuss if you want bypass isolation should the transfer switch ever fail, or you want to do maintenance on the transfer switch. Additional considerations for automatic transfer switches include whether you want a 3-pole with overlapping neutral or 4-pole. These days, 4-pole, which has a true switch neutral, is the most common application of ATS, but you need to look at that. Next are the topics of load shedding and load sequencing. If you can imagine that you've got different types of loads, we talked about emergency, optional, legally required, or in a hospital, there might be multiple branches of different types of critical loads. You may want to assign priorities to the automatic transfer switches. So if there's an overload, if there's a starting, we talked about the 10 seconds and the 60 seconds, you want the emergency loads to start first. So you might prioritize the automatic transfer switches to switch on the load. The generators come on, whether it's one or paralleled, but the emergency load transfer switches come on first, legally required second, optional later. You also have the ability for load shedding, should there be overload or other conditions, to shed the non-emergency load first. Lastly, with ATSs, you want to talk with your vendor and your specifier about the make before break or break before make. Basically, on the return, this usually applies on the return when utility power returns, and you're going to transfer back while the generators are running to utility power. On a make before break, it's the most continuous way to maintain the power as you transfer over. For a millisecond, the emergency power and the utility power are actually connected while it transfers over. On a break before make, there's actually an interruption, a small interruption of the power to move over. Just make sure you coordinate with the utility, because they don't like your on-site power sources paralleling even for a millisecond with your on-site power. Speaking of paralleling is becoming more and more prevalent these days as facilities require more and more backup power. The issue used to be that the controls were very complicated and clumsy. The generator vendors have become much more sophisticated. The controls have become digital, much easier to control, much faster. So there's a lot of options with paralleling that didn't used to be in the past, and that also allows you to specify multiple generators so you can get redundancy. So you can have, instead of one big generator, maybe 2 smaller generators and get some backup in there. There used to be concerns about the startup time, and some local authorities still have this in terms of the generators coming online, synchronizing within that 10-second emergency requirement, particularly when you're mixing emergency and standby and optional loads. Again, load sequencing can be a way to show that you are prioritizing and making sure that 10 seconds is handled with the first generator or second generator that comes online. But again, a lot of options for paralleling these days. Selective coordination. Basically, selective coordination means when there's a fault in the electrical system, does the breaker where the fault occurs trip first? You don't want breakers higher up in the system that serve multiple parts of the loads to trip. So on emergency requirements under Article 700, you do have to do a selectively coordinated system. Typically, you will do a coordination system, a rough coordination system as a designer, and require a final coordination from the contractor or vendors once all the breakers have been shipped to the site and you know what's going to be installed. 701 article also requires, for legally required standby, also requires a selectively coordinated system. Testing is an important thing. If you want a generator, you've got to have critical power. There are a lot of different types of tests. You can specify factory testing. Usually the generator vendor will do these normally. You have on-site tests that can be done. You can go and do factory witness testing if that's a possible budget. Acceptance testing in the field by NETA standards or by a NETA testing agency is a great way to ensure that that there was nothing missed at the factory, nothing missed in the field when these generators were installed. Commissioning is functional performance testing. Rather than looking at, say, if the right fuse is installed, the commissioning agents will run the systems through their paces. Most often, the common thing you think about is a pull the plug test. Everything's installed, the generators, the facility's almost ready to go. You turn it on and someone goes and flips basically the switch, turning off the utility, and watches at various points in the emergency and standby systems if the load functions. The next thing that is required by code, some of the acceptance testing and commissioning is often optional, is the ability to load bank the test. The generators have to be load banked. They have to be tested regularly. If they're not tested under load, then they every 30 days, then there's requirements for load testing, either under load or using a load bank. And all of these are outlined in the various codes and standards. Next, I'll turn it over to Dan to talk about mechanical.
Thanks, Brian. All right, so today is part of the mechanical design portion of engine generators. We're going to cover the following topics: the location, the fuel systems, cooling and ventilation, seismic and vibration, acoustics, and we're going to touch a little bit on emissions of the generators. First of all, we're just going to go over the mechanical components that we're worried about as part of the engine generator. The first component that we see in the lower left is the base rail. This is the rail that the engine generator sits on, and all of its weight comes down on that rail, and that rail is either supported directly to a concrete pad, or there will be vibration isolators underneath it to isolate it from the pad. Next component, moving left to right, is the controller, which Brian's mentioned, which controls the engine and does a lot and keeps it's running at speed and turns it on and off when needed. The next component is the alternator, and that's what actually makes the electricity. That's the piece of equipment that the engine is spinning the axle to make sure that the electricity is generated there. Then the next component, moving over from left to right, is the combustion air intake. That's the source. That's the place where the engine pulls its air from the room in which it's located in into the engine and uses that to combust the diesel or gas that is going into the engine. The next component is the exhaust. That's where the air and the products of combustion exit from the engine and go out of the building. Right now, we're just showing where the connection is and not the whole exhaust pipe, vent piping. Next component is really, the heart of the generator, which is the engine. And, that's what's moving the alternator, and that's where that's what's generating all the power in the engine, and where all the mechanical systems are basically there in place to make sure that that's operating properly. And then lastly, on the right-hand side is the engine-mounted radiator. That basically comprises, similar to your car, of a fan in a radiator coil to remove heat that comes off of the engine. We'll move on to the next slide. So getting into some of the fuel systems for the engine generators. As Brian kind of mentioned previously, the NEC requires NEC Emergency Article 700 and legally required standby systems be provided with fuel for a minimum of 2 hours. So that means on-site storage means the fuel is literally there on-site and isn't off-site. However, the authority having jurisdiction may grant an exception to this requirement where there's low probability of simultaneous failures of off-site fuels, like natural gas and electrical power failing at the same time. NFPA 110 defines the minimum operating time in an emergency power system must be capable of operating, which determines the fuel storage volume. So for a natural gas power generator, you're not worried about how much fuel is being stored. However, for a diesel fire generator or a propane fire generator, this comes into your design concepts very much. Some of the other considerations for the fuel selection is what's available. Are you going to be allowed to put diesel on site? Does natural gas serve the area you're in? Or will propane be acceptable? And then the other component is what fuels are allowed. And that usually gets into what are you trying to do with your engine generator? Are you just doing emergency power, or maybe are you doing some peak shaving? If you're doing peak shaving, then you also have to get into other ideas of what's the EPA or your local jurisdiction going to allow as far as emissions. The EPA typically allows 100 hours per year for maintenance testing and demand response. So anytime that you want to spend, you get 100 hours on an emergency generator to allocate towards that. And however, if you go over that, then your system becomes less of an emergency generator and more of a power. It's considered not an emergency generator, but a power making generator, and subject to tighter restrictions. However, you should check your local requirements when considering paralleling or peak shaving with your engine generator. Now getting into the diesel fuel systems, NFPA 30 is used as the code for storage, handling, and the use of diesel fuel. That code is going to tell you everything you need about piping, the tanks, and accommodating storing and handling the fuel to your engine generator. Go over normal vents, emergency vents, fill alarms on tanks when they're at 90% so the operator doesn't fill it, and mechanical fill valves that will actually stop tanks from being installed at 95%. Then the other options become, how are you going to store your diesel fuel? Well, you can either store diesel fuel in an underground storage tank or an above ground storage tank. Underground storage tanks have advantage that they save space and provide that gravity drainage back to the fuel system. And all the piping can be installed above them. So everything can drain back to them. However, their disadvantage is that the EPA regulates that these tanks, if over 110 gallons, need to be monitored and reported annually by the customer for perpetuity. Above ground storage tanks are not subject to that same scrutiny by the EPA because their potential for accidental release is considerably less. However, they come with additional challenges. Now looking at a diesel fuel piping system, we'll kind of go through what are the main components. This is your typical arrangement for the diesel fuel piping system. You'll have a bulk storage tank, a day tank, and an engine generator. The whole reason for the day tank is to make it easy for the pump on the engine generator to pull fuel out of the tank and run it through the engine. Whatever fuel the engine does not use, it will put back into the day tank, which is located very close by. So you don't have to worry too much about overcoming system pressure losses. However, when considering the design of these systems, you have to run your hydraulic calculations on them. And bear in mind that these systems are, due to the nature of all tanks being vented to atmosphere, these are all open systems. So you have to actually pull fuel from one side, and then your pump has to be able to push it through the system and return it to wherever it's going. And when considering how much suction lift is on a pump, note that because diesel fuel's specific gravity is less than water, it can't pull as far as it can't pull the diesel fuel up in suction as far as water, and it's limited to about 15 inches of mercury. And if doing a system with large suction lifts, consult the pump vendor to make sure that whether you need a single stage pump or two stage pump. Moving on to the next slide. So another manipulation of that previous diesel piping system is the belly storage tank. This tank has large advantage that you can remove the day tank because the engine generator is co-located with the day tank. However, the fuel tank, the volume of the fuel tank can be a limiting factor of how large a fuel tank you can get to sit underneath the engine generator. Another limiting factor is that these systems usually are required to be installed outdoors. However, they come as a standard offering with an enclosure for outdoor package generators. Moving on to the next slide. Now getting into some other systems, some gaseous fuel systems. Natural gas is probably the most popular fuel system for a commercial generator. These generators are typically larger in footprint than a diesel generator for the amount of power that they output. However, they have a more difficult time responding to changes in load. And natural gas generators must be fitted with the gas trains to safely fire. And this is all dictated by NFPA 54 and NFPA 37, which is specific to engine generators. The gas trains include a sediment trap, isolation valve, pressure regulator, low gas pressure switch, automatic safety shutoff valve, leak test, another automatic safety shutoff valve, another leak test valve, and then a high gas pressure switch. These are all the components needed to safely move gas from the pipe main into the engine generator. While we don't have to worry about fuel storage on a natural gas system, we do have to worry about making sure that we get that we have enough quantity of gas at the pressure needed to fire the generator. The generator vendor will tell you what the upstream pressure they need at the natural gas train is to get to the generator, typically 7 to 14 inches of water column. However, a lot of times you'll feed a natural gas engine generator with high pressure gas, and then regulate it down on the valve outside of the generator, and then put it at low pressure at the 7 to 14 inches at the generator. This can run into problems because you have two pressure regulators in series with each other, and they might start doing some hunting. The mitigation for this is to oversize the line feeding between the two regulators to allow a little bit more gas in that area, so that the regulators can work together and smooth out their operation, or to put in the accumulator tank in that piping to get the generators so there'll be some buffer. Next slide. All right. Looking at another type of gaseous fuel system is liquefied propane gas. Propane fire generators are similar to natural gas generators, but their capacity is limited due to the market availability. They typically max out around 250 kW. Outdoor generators with above-grade tanks may not have sufficient, and another issue is working with outdoor fire generators with above-grade tanks may not have sufficient area in cold climates to feed vapor-fired propane, so a vaporizer may be required. Basically, what a vaporizer does is it heats up some propane to keep pressure in the propane tank, so that the propane tank will have enough propane will be vaporized to get it to flow from the tank into the generator. Now we'll look at some cooling and ventilation issues. So engine generators typically have water-jacketed engines that reject a large portion of the engine heat to the radiator. The radiators on the package engine generators are air-cooled. However, air and water-cooled radiators can be used to reject engine heat. However, if these types of radiators are used, they're typically remote-mounted. Despite the engine water jacket, significant amounts of heat are radiated from the engine and the electric generator, and these items are air-cooled. So the way a normal package engine generator works is that it pulls the heat off of the generator and off of the engine and out through the radiator, and also picking up the heat from the water cooling jacket in the engine to blow it out of the space. And that's how the typical generator is done. If you're going to use a remote radiator, you have to remember to also capture the generator heat and engine heat. Some other considerations on the package engine generators are to ensure that the proper airflow distribution must be given to ensure the cooling airflow absorbs the generator and the engine radiated heat. So as you can see in the graphic below, the preferable configuration is to bring cool air in from the left side and out through the right side as hot air. The poor location would be to short circuit the air from below the generator, as I'm showing in this graphic, and then out just across the radiator, because you wouldn't be getting the heat from the alternator in from the engine. Another consideration is the size of the air intake openings must be considered. You must also consider the combustion air to be pulled through those openings to make sure that the fan and the fan in the radiator has enough capacity and static pressure to overcome that load. Moving on to seismic and vibration. Where required, and usually this is done, you review ASCII 7 to see where is required, where seismic certification is required for the engine generators. Because engine generators, let's face it, they're there because something's gone wrong, and that something could very easily be an earthquake. So making sure that they're seismically rated is important. And then moving on to the vibration aspect, engine generators must be vibration isolated from the structure housing them. Integral isolation between the engine and alternator and the base rails must sit on external vibration isolators. We must make sure that when that stuff is vibration isolated, we must make sure that the radiator is connected via a flexible connector to the fan shroud or an exhaust louver. And the fuel piping transitions to the engine must be through flexible hoses, and the exhaust pipe or vent pipe must be connected with a flexible connector. Additionally, the structure the engine generator is mounted on must be analyzed to ensure its natural frequency does not overlap with the natural frequency of the engine generator system. Looking shortly at some acoustics, engine generators are loud, and the best method to mitigate the engine noises are the following. Silencers on the exhaust, walls with minimally sized openings and significant mass. And to add distance between the engine generator and the offended party. For every doubling of distance, the sound level reduces by 6 decibels. Unfortunately, employing each of these methods above adversely affects the engine performance, except for the third bullet. So go for that if possible. Some items to consider when implementing those is adding normal critical or hospital silencers to the exhaust. Consider the additional pressure drop these devices have on the exhaust flow. Where large airflows are required for cooling, consider acoustic louvers and their intake and discharge plenums to force a redirection of sound waves. And lastly, consider installing an engine generator inside a building or concrete enclosure instead of sheet metal enclosures to mitigate sound. Now I'll pass it over to Brian.
Thanks, Dan. So as Dan mentioned, one of the options you have with placing the generators is inside or outside. We have to work with the architects. It's a complicated relationship. One of the things you have to look at, and I know that it can be challenging to determine the size of the generator early in the project, particularly when you're going beyond emergency systems, which are easy to estimate for a building. When you start talking about standby and or owner wish list optional loads. But you really need to, especially if the generator is going to be located inside, you have to look at the room heights. You have to have adequate to put that silencer that Dan talked about, the different type of silencer, to put access and clearance around them. And you have to also look at how the generator will get in and out of the building, typically through the louvers, egress in and out from around the generators, and those louver locations. Coordinating with the architectural, louvers can be semi-decent looking. You have to coordinate with the architect on where they go in the building, their size, how they're controlled. You can also see here, the exhaust has to be coordinated with the building. Obviously, you don't want to put that exhaust near air intakes, air handling units, open windows. So here you can see on the right that we had on a project, we had to run the generator exhaust really high up the building to get it away from contaminating air streams. You also have to coordinate with your fire protection engineers. Are sprinklers required in generator rooms? Under NFPA 13, yes, they are, unless the room is rated for 2 hours. However, the local authority having jurisdiction may not allow these. Example may be Chicago. Fire detection, you want to have fire detection, but you certainly don't want to put smoke detectors in electrical rooms, generator rooms. You want to look at heat and flame detectors. When you're determining if they're going to be put outside, which is a common way to avoid building extra space, you definitely want to talk with the owner and their maintenance staff to know that the generator is located outside, particularly in cold weather or storm climates where maintenance staff may have to go outside to work on a generator, which is not preferred. Dan talked about those belly tanks. In this photo, you can see a pretty high belly tank. You're really going to have to consider how will they get to the generator up above to do servicing, testing, and inspection. Often on larger generators, we build a platform around that belly tank so that you can get up and do the servicing. Skinned units are available from the vendors, typically up to 500 kW or more on the generators. When you go larger than that, usually the vendors send the generators out to custom fabricators of enclosures. Those can be walk-in enclosures that could compromise between indoor and outdoor. They can be custom. They can have sound attenuation on those enclosures. And even when it's located outside, you have to look at access and clearances, particularly under the NEC. Structural, you have to coordinate with structural, whether it's indoor or outdoor. You have to give them the weights, the vibration criteria, the movement. You have to look at the floor and pad construction, vibration isolation, particularly if they're located in buildings where vibration may be a concern to sensitive equipment outside the room. You do have to look at the emissions and EPA tiers. Just know that this is a very complicated topic and it's very local. California can be different than Iowa with regards to emissions and what tier you have to do. So you have to look at these tiers. If you get into high tier ratings, the size of the generator overall increases as they start to do after treatment of the exhaust. You can look at sound, like we talked about, sound attenuation when you're outside on sites, particularly if there's a residential or other businesses nearby at the property line. There are certain sound criterias and all sorts of custom enclosures you can do to have that done. So in conclusion, we went over generator components. You understand the basic components of engine generators. We talked a little bit about the code classifications and requirements. We went over power ratings, automatic transfer switches, cooling and ventilation, fuel sources, noise and ventilation, and coordinating with your other design team members like architects and structural engineers. Thank you.
All right. Well, thank you, Brian, and thank you, Dan. That is a lot of information. Let's take some questions now. Please type your question into the Ask a Question box on your screen and type the presenter's name before your question so that I know who should answer it. We will get to as many questions as time allows, and questions that we don't get to will be posted online with answers at www.csemag.com. That's cscmag.com. And to download these presentation slides, which do have additional resources on the slides, please click on the event resources on the left side of your screen. And as a reminder, you may earn one AIA CES approved learning unit for this event. You do need to pass a 10-question exam. To take that learning unit exam and to download your AIA CES certificate, please use the Learning Unit Exam tab option at the top of your screen. The exam will open in a new browser window. And then, of course, if you haven't heard of CFE EDU, you can click on the link in the downloadable PDF for some free courses. There are several courses. One is on smart buildings, one's on critical power systems, and there's another on transformers, UPSs, and switchgear. These are all free of charge, and registration is required. You can watch them or attend these courses at any time. They're all on demand. All right, so let's get to some questions. Dan and Brian will now answer some of these questions. Please, if you could type their name before the question, I will know who to direct it to. All right, Brian, we are going to kick this off with you. The first question: are generators available in medium voltage ratings, and what are some of the considerations?
Yes, it's a good question. Generators are available in medium voltages, typically 5 kV and 15 kV class rated generators. What we're seeing is that because the need for backup power, particularly optional, not necessarily emergency, but backup power is increasing, Larger facilities, hospitals, mission critical facilities, laboratories, in areas of the country where we've seen utility outages last days with fires and ice storms and unexpected environmental weather events. We're seeing more and more power. So medium voltage is definitely something you want to consider when you've got a lot of power to move. If you think about a 2000 kVA or even a 2500 kVA generator at 480, that's a lot of copper coming out of that generator. Typically, generators are going to be located outside the building, but they might be inside the building too. Bringing all that copper over, duct banks, enter into the building. Medium voltage, you shrink the wires by going to the higher voltage. It's much more efficient. The generators themselves are not that much bigger. And the cost is maybe 10, 15% more than a 480 volt generator. The gear is going to be more expensive to switch and transformer. You're going to have to add a transformer at some point. But it really can make sense for medium voltage generators to be considered.
All right. Thanks, Brian. Dan, this next question is for you. Please outline the advantages and disadvantages of natural gas gensets versus diesel gensets.
Thanks, Mara. Some of the advantages of natural gas gensets, like I kind of went over before, are that you don't need to plan for having storage on site with natural gas gensets, and they're more opportunity to do load shedding with utilities than diesel gensets. However, they're physically larger machines because they require a larger footprint to put out a similar amount of power. Diesel gensets are more compact, and while you have to store their fuel on site, you always know that you have that fuel on site, and you know that that service can't be interrupted in the event of an emergency. Mara?
Yeah, got it. Good. Thank you very much. Let's see here. Brian, I'm going to send this next question over to you. Does a fire pump have to be connected to the temporary source of power? I know you touched on that a little bit. If you could provide a bit more detail.
Really, if you look what was behind the NEC addition in Article 700 about the temporary hookup box, particularly on a single generator that's providing your emergency power, that generator can fail. It can need repairs. It can need significant maintenance. There's any number of reasons why that generator might be offline. The owner may wish to perform some maintenance on it that it knows it needs to do. And the fire pump is an emergency required load. You cannot leave the facility generally unprotected. There are some instances where I've seen facilities under construction or in certain stages where they can provide a fire watch that is around the clock, people monitoring the facility. But my answer would be yes. When you design the electrical system and you're putting in that hookup box, the hookup box should be just like the rest of the electrical system and connect all the emergency loads connected to it.
Okay, got it. Dan, let's take another question here. So this is going back to diesel engines. Does a diesel engine always pump in more fuel than it needs, first of all? And then, is that why you need a day tank here? And then the second part of this question is, which system controls this? Because there are engines that are compression ignition based. Can you go into more detail about that?
Yeah, sure. So basically, the diesel engines, they take a certain amount of they have a fuel pump mounted on them, and the fuel pump pulls fuel out of the local fuel storage tank, be it a bulk tank or a day tank. It pulls that fuel into it and then pushes it either into the engine, and then the valves on the engine will basically determine how much fuel goes in, and then the remainder of it will push back out to the local tank, whether it be a day tank or bulk tank again. So that pump is always pumping a constant flow of fuel, despite how much fuel the engine itself is consuming. So you do always have to have a certain amount of fuel going, a place for the return line of the engine to put its fuel.
All right. Yeah, a lot of information there. Thank you. All right, Brian, this next one's for you. And we're going to talk about generator sizing here for a second. So did you say the recommended generator sizing should be based on kilowatts? So can you go into a little bit more about that? I mean, there's a lot of ways to look at this.
Right. So going back to the 0.8 power factor, and it's just the way the generators have been rated for forever. If you take the typical math as you take the kW, divide by 0.8, and you get your kVA. Okay, that is not the power that you're going to get if you have a 0.9 power factor facility. So you're going to do two things. In the early stages of a project, you're going to be doing quick calculations, maybe spreadsheets, maybe even hand calcs, maybe even estimates of how big a generator you've got. At that point, I would just tell you to focus, just engineering good practice, to skip the kVA rating. Whatever kVA load you have, if you're thinking in terms of kVA, just use the kW rating of the generator to pick that, because a lot of the emergency loads, for instance, lighting, one power factor. And then you're going to run, as you get into design development, final construction documents, you're going to run your detailed load calcs, and you can fine tune the generator, and you can look at the kW and the kVA based on the power factor and do the engine generator selection, for instance, using the generator vendor's free software. I hope that explains it.
Yeah, I think so. If not, we can come back to another question. And if you do have a question, please type your question into the Ask a Question box on your screen. And please do type the presenter's name before your question so that I know who should answer it. And we'll get to as many questions as time allows today. All right, Dan, moving over to a question for you. Let's see here. Should louvers be mechanically operated with an electrical actuator, or should the louvers be fixed? Is that one that you can take?
Yeah, sure. In my practice, what I've typically done is the discharge louver from the radiator is gravity, is a backdraft damper, which is pushed open by the pressure of the fan, and the intake louver would be electrically powered. However, there's no requirement not to have either of these louvers as either gravity or electric operated. The advantages of the electric operated dampers are that they open and that they don't increase the amount of static pressure that the fan must overcome to flow the amount of air. However, now you've got a component added into the system that can fail, the electric actuator. These dampers and their actuators need to be configured such that they're power closed and off when they're unpowered, when you're configuring the controls for them, so that when power is lost, basically what needs to happen is that the damper needs to open on the power when normal power gets lost, and then when the engine generator comes up and running, you have to have a relay in line that keeps that damper actuator open while the engine generator is running. And then once the engine generator turns off, that relay has to reset, and then the damper will be allowed to close until normal power is lost again.
I might add, Dan, too, I saw a question about cold climates. I think we have a few Canadian viewers on our webcast today. One of the things we've encountered, too, on the air intakes, Dan mentioned there's two types of air. You have air for heating and you have air for combustion. In extremely cold climates, you might want to stage the air intake into a room or recirculate the air from the discharge, I think, as Dan mentioned, so that you don't fully open your air intakes and bring in minus 10-degree air into the room immediately. So that's another louver control sequence you might want to look at.
Yep.
Cool. Yeah, thanks for adding that information, Brian. So this next question, Brian, is actually a two-part question. I can repeat any portion of this. First part, when is a load bank required to be part of a generator? And next, when is a load bank required to be part of the generator package? Is that the same thing? Can you describe that for us?
Yeah, it's independent of whether the generator is located inside or outside. Basically, there's a whole thing about load bank testing, particularly in the NFPA. There are two ways you can test your generator. You can just turn it on. Okay, does the generator start? Does it warm up? Does everything look okay? And that's a requirement that you can, or that's a thing that you can do every 30 days, just turn the generator on. The question is, how do you place load? They want you to place load on the generator. So then we get to the next step. Are you going to actually put facility load on? There's some facilities where it's not so critical, and they're willing to go ahead and turn the generator on and put the actual loads that would fall on the generator in an outage on the generator. If you can't do that, and all you're doing is turning the generator on, the code requires you to put actual load on the generator. And there's some complications about how much load, how often in a year, but eventually you have to put load on the generator. So you have two options then. You can put this hookup box, and you can hire an agency to come in every so often and actually place a resistive or reactive load. And I saw that as a question. It can be either. The code doesn't specify, although I do like having some reactive load. Or you can install the load bank permanently, so you never have to go to an agency. You never have to have a contract with someone. You've always got the load bank outside where you can test the generator on the load. And you have to keep all those records and keep them available only for emergency or legally required standby, not for optional generators.
Okay. So speaking of emergency, here's a question for you. And Brian, this one might be for you. Did you address location and possible code requirements for emergency stop push buttons or e-stop buttons? Did you talk about that at all?
I didn't. That's been an issue, particularly in mission critical facilities, for a long time. The emergency stop buttons, there's a requirement in the code, particularly about data centers, that talked about underfloors and cables. But historically, just from a practical standpoint, my experience has been that those emergency stop buttons are something that the local fire marshal loves to have, because if there's an emergency, a fire in a building that has generators, they want to turn the utility power off before they go in there with hoses and swinging axes and having the guys running around, right? So if you've got a generator or even a UPS running, there could be live power within that facility. So often it's a discussion with the fire marshal about having these emergency power offs. The second thing is that some clients, data centers again, just have a panic that those emergency power off buttons could be accidentally pushed during a situation. There are ways to overcome this, putting the emergency buttons behind a locked enclosure, behind a break glass enclosure. There are ways to protect this so there's not accidental stop. But in my mind, it usually comes down to the local authority having jurisdiction, particularly the fire marshal, understanding what type of generators you have on site and how they operate.
Okay, good. Thank you. Dan, this question's really quick. Just referencing back to ASCE 7. You said that was a good reference for seismic considerations. Is that correct?
Yeah, so ASCE 7 will kind of give you what needs to be, is what's often referenced in the local building codes as the structural code, and that'll reference mechanical and electrical equipment and what needs to be operated and what needs to be braced after a seismic event.
Okay, good. Thank you. All right, we've got time for just one more question. Brian, you get the last one. And this one is kind of a long one, so bear with me for a moment here. When you have a fire pump connected to the generator, does it make sense to utilize a 4-pole ATS for non-fire pump branches? Because the fire pump ATS is 3-pole.
Yes, a good question. The answer is you only need a 3-pole transfer switch. The question comes up a lot when we're designing facilities, particularly industrial or certain types of projects where you're not going to need panels or switchboards or gear with a neutral at all. You can just use 3-phase panels, three-phase switchboards for mechanical loads. Often in the way we design it, unless it's specifically a large industrial facility, we'll just put 4-wire switchboards and panels everywhere. And so we just put a 4-pole transfer switch. But the answer is no. And typically you can use a 3-pole, and the transfer switches that come with fire pumps are 3-pole.
Okay, got it. So I'd like to wrap up by thanking these extraordinary subject matter experts, Brian Redder and Dan Flaherty, for sharing their extensive knowledge of generators and generator design. And I'd also like to extend a special thank you to sponsors Pritchard Brown, ASCO, and Kohler for supporting this education session. Before we go, we need your feedback to improve on future education sessions. A short survey will pop up on your screen as soon as this webcast ends. Please take a few seconds to complete it. Finally, on behalf of Consulting, Specifying, Engineer, and CFE Media and Technology, thank you for joining us today. And we'll see you again at the next education session. Goodbye.